history of the world, only a few generations have been granted the role of defending freedom in its hour of maximum danger. I do not shrink from this responsibility. I welcome it. I do not believe that any of us would exchange places with any other people or any other generation. The energy, the faith, the devotion which we bring to this endeavor will light our country and all who serve it. And the glow from that fire can truly light the world. And so, my fellow Americans, ask not what your country can do for you. Ask what you can do for your country. My
Welcome to Musings of a Cigarette-Smoking Man, a podcast where history, reflection, and curiosity fuse into an intimate conversation about some of humanity's boldest adventures. I'm your host, inviting you on a journey through space and time, tracing the legacy of NASA and the American space program, while gazing forward to the boundless horizons that still await us. There's something profoundly nostalgic about looking back at where it all began. The flickering black and white broadcasts of lunar landings, the gripping tension of mission control rooms, the voices crackling through radio waves. All of these moments are etched deep in the collective memory. As I light up a cigarette and settle into these musings, I find myself both humbled and exhilarated by the sheer scale of what humans have dreamed and dared to achieve beyond Earth's atmosphere. Today's episode will unfold as both an exploration and a reflection. We'll journey through the milestones that marked NASA's rise, from the fiery liftoffs that launched us to the moon, to the quieter triumphs of scientific discovery and technological innovation. Along the way, we'll consider the larger-than-life characters, the unsung heroes, and the spirit that fueled America's quest to reach beyond the stars. This isn't just history, it's a living story. We'll also look ahead to the future NASA envisions, the Artemis missions returning us to the moon, the dreams of Mars exploration, and the new frontiers in commercial spaceflight and international cooperation. These visions capture the restless spirit of discovery still burning brightly in the 21st century. Now, as this narrative unfolds, expect to hear moments where we pause for brief interludes, commercials that celebrate craftsmanship and creativity, perfectly weaving into our themes of dedication and exploration. These segments, from Black Rifle Coffee to skillful tools like Skillcraft pens, sites like allpoetry.com, Moleskin notebooks for the inspired writer, and Monarch Holdings International, will offer you something to savor, whether it's a morning brew or an invitation to craft your own stories. So, sit back, light up, grab your favorite adult beverage, and join me as we embark on this odyssey, one that's part history lesson, part memoir, and part poetic musing about what it means to dream, explore, and create under the vast, starry canvas of space. The dawn of American space exploration, foundations of NASA. All right, settle in. Our journey through the American space program begins not with a giant leap, but with a jolt, a shockwave that rippled across the United States on October 4th, 1957. On that crisp autumn day, the Soviet Union successfully launched Sputnik 1, the world's first artificial satellite, into orbit. It was a small metallic sphere beeping its way around the Earth, yet its significance was immense. To many Americans, it wasn't just a scientific achievement by a rival nation. It felt like a direct challenge, even a threat. For years, there had been discussions, studies, and scattered efforts in the U.S. regarding rocketry and spaceflight. Organizations like the National Advisory Committee for Aeronautics, NACA, established back in 1915, had been conducting cutting-edge aeronautical research for decades. NACA's wind tunnels, laboratories, and brilliant engineers were foundational to American aviation, but their focus was primarily on atmospheric flight. The idea of space exploration, while certainly dreamt of by scientists and visionaries, hadn't been elevated to a top national priority. From aeronautics to astronautics, the birth of NASA. Sputnik changed everything. The sudden realization that a geopolitical rival had beaten the U.S. into space ignited a furious debate about America's technological standing, educational system, and military preparedness. There was a palpable sense of urgency, a call to action. President Eisenhower and Congress recognized the critical need for a unified national space program, distinct from the various Army, Navy, and Air Force missile programs that were already underway. The question wasn't just about catching up. It was about establishing clear national leadership in this new vital domain. The consensus quickly formed that a new civilian agency was required to oversee non-military space activities, leveraging existing expertise while providing a clear, forward-looking vision. This led directly to the passage of the National Aeronautics and Space Act, signed into law by President Eisenhower on July 29, 1958. This act dissolved NACA and transferred its assets, personnel, and expertise, along with various other government space research efforts, into a new entity, the National Aeronautics and Space Administration, or NASA. NASA officially began operations on October 1st, 1958. Its founding principles were ambitious and far-reaching. The Act mandated that activities in space should be devoted to peaceful purposes for the benefit of all humankind. Its core goals included the expansion of human knowledge of phenomena in the atmosphere and space, the improvement of the usefulness, performance, speed, safety, and efficiency for aeronautical and space vehicles, the development of operation of vehicles capable of carrying instruments, equipment, supplies, and living organisms through space, the establishment of long-range studies of the potential benefits to be gained from the utilization of aeronautical and space activities for peaceful and scientific purposes. The preservation of the role of the United States as a leader in aeronautical and space science and technology. The most effective utilization on the scientific and engineering resources of the United States, with close cooperation among all interested agencies of the United States in order to avoid unnecessary duplication of effort, facilities, and equipment. It was a mandate for exploration, innovation, and national leadership, all framed within a spirit of peaceful scientific endeavor, even while the shadow of the Cold War loomed large. Taking the first step, Project Mercury. With NASA established, the race was well and truly on. The immediate priority was clear: put an American into space and, crucially, into orbit. This became the focus of Project Mercury. Announced in 1958, Mercury was a crash course in human spaceflight. Its objectives were relatively modest by today's standards, but utterly revolutionary at the time. 1. To put a manned spacecraft into orbital flight around Earth. 2. To investigate man's ability to function in space. 3. To recover both the man and the spacecraft safely. NASA selected a group of 7 test pilots in April 1959, the famous Mercury 7. These men, including names that would become household legends like Alan Shepard, John Glenn, and Gus Grissom, embodied the courage and daring required to strap themselves atop rockets that were, in those early days, notoriously unreliable. As Tom Wolfe would later describe in The Right Stuff, they were pushing the boundaries of the unknown. The path was challenging. The Soviets launched Yuri Gagarin, the first human in space, in April 1961. Just weeks later, on May 5, 1961, Alan Shepard made his own historic flight aboard Freedom 7. It was a suborbital hop, a ballistic trajectory up and down, but it proved Americans could go to space. The real triumph for American orbital flight came on February 20th, 1962, when John Glenn circled the Earth 3 times aboard Friendship 7. The nation was glued to their radios and televisions, holding its breath with every pass over tracking stations. Glenn's safe return was met with an outpouring of national relief and pride. Building capability, Project Gemini. The Mercury program was a vital first step, but getting a man into space and orbiting a few times wasn't enough to reach the moon. NASA needed to learn much more. This led to the next critical phase, Project Gemini, which ran from 1961 to 1966, with crewed flights primarily in 65 and 66. Gemini's purpose was explicitly to bridge the gap between the simple Mercury missions and the complex lunar missions of Apollo. Its objectives were more ambitious: to subject men and equipment to spaceflight for extended periods, up to 2 weeks, simulating a lunar mission duration; to understand and demonstrate rendezvous and docking in orbit, essential for connecting modules on the way to the moon; to perfect techniques of re-entry and landing; to perform spacewalks, extravehicular activity, EVA, and understand how astronauts could work outside the spacecraft. Gemini missions, often carrying 2 astronauts, hence the name, referring to twins, were groundbreaking. Ed White performed the first American spacewalk during Gemini 4 in 1965, a truly iconic moment. Missions like Gemini 5 tested endurance, and Gemini 6A and 7 performed the first rendezvous in space, flying in formation just a foot apart. Gemini 8 achieved the first docking with an uncrewed Agena target vehicle, though it ended with a dangerous spacecraft malfunction that required rapid, skillful intervention by Neil Armstrong and David Scott. These Gemini missions were tough, demanding, and often fraught with risk, but they were absolutely indispensable. They pushed the limits of both human endurance and technological capability, proving that astronauts could live and work in space for extended periods. perform complex maneuvers like docking, and conduct tasks outside the spacecraft, all necessary prerequisites for a lunar landing. The spirit of this era was one of relentless pursuit. There was a sense that failure was not an option, that the eyes of the world were watching, and that America's future technological leadership, and perhaps even its security, depended on the success in space. It was a time of immense innovation, rapid learning, and forging a national identity tied in part to looking upwards. Apollo triumphs, building a legacy on the moon. All right, let's shift our gaze from the foundational steps of Mercury and Gemini to the towering ambition they paved the way for, Project Apollo. If Mercury was learning to walk in space and Gemini was learning to run and maneuver, Apollo was the sprint to the finish line, a monumental race to reach the moon. This wasn't just the next logical step, it was a direct, audacious response to a challenge laid down by President John F. Kennedy in May 1961, just weeks after Alan Shepard's suborbital flight. Kennedy stood before Congress and declared, "I believe that this nation should commit itself to achieving the goal, before this decade is out, of landing a man on the moon and returning him safely to the Earth." It was a goal so audacious, so technically challenging, that it seemed almost impossible. At that moment, the United States had barely put a man into space for 15 minutes. Yet, this declaration ignited a singular national purpose, focusing an unprecedented level of resources, intellect, and effort on one seemingly insurmountable task. The scale of ambition, the Apollo program. Project Apollo was unlike anything humanity had ever attempted. It required inventing entirely new technologies from the ground up. How do you build a rocket powerful enough to escape Earth's gravity and carry multiple tons to the moon? How do you navigate across 250,000 miles of empty space? How do you land a fragile craft softly on an unknown, cratered surface? How do you keep humans alive, healthy, and functional in the vacuum of space on an alien world? And critically, how do you get them back? The engineering challenges were staggering. They necessitated breakthroughs in propulsion, guidance, navigation, life support, materials, science, communications, and computing. The sheer scale of the project was immense. NASA's budget grew exponentially, employing hundreds of thousands of people across universities, private companies like North American Aviation, Grumman, and Rockwell, and government centers. It was a national undertaking, a truly collaborative effort on a scale rarely seen. Central to Apollo was the development of the mighty Saturn V rocket, designed under the leadership of Wernher von Braun and his team. The Saturn V was a three-stage behemoth, taller than a 30-story building and capable of generating over 7.5 million pounds of thrust at liftoff. It remains one of the most powerful machines ever built. Its purpose was to lift the complex Apollo spacecraft components into orbit and then propel them towards the moon. The Apollo spacecraft itself was a complex assembly. The command module, CM, control center and crew quarters for most of the mission, designed to re-enter Earth's atmosphere. This was the only part that returned to Earth. The service module, SM, attached to the CM, containing propulsion, power, and life support for the journey to and from the moon. The lunar module, LM, the dedicated lander, designed only to function in the vacuum of space and on the moon's surface. It had two stages, a descent stage for landing, and an ascent stage for returning to orbit. Developing these components simultaneously, testing them, and ensuring they could work together seamlessly was an engineering and management feat of incredible complexity. Overcoming adversity, challenges, and setbacks. The path to the moon was not smooth. It was marked by intense pressure, tight deadlines, and profound tragedy. The most significant setback occurred on January 27, 1967, during a launch rehearsal for the first crewed Apollo mission, Apollo 1. A fire erupted in the command module cockpit on the launch pad, resulting in the deaths of astronauts Gus Grissom, Ed White, and Roger Chaffee. The fire was a devastating blow, forcing NASA to halt the program, conduct a thorough investigation, and completely redesign the command module to improve safety and reliability. This tragic event, though heartbreaking, led to crucial improvements that were essential for the safety of future missions. Beyond the fire, there were countless technical hurdles to overcome. Developing the guidance computer, building reliable life support systems, perfecting the lunar landing radar, each component presented unique challenges that required innovative solutions, often pushed to the very edge of technological capability at the time. Paving the way, early Apollo missions. After the Apollo 1 tragedy, the program resumed with uncrewed test flights, demonstrating the Saturn V's power and the spacecraft systems. Apollo 4, 5, and 6 were critical steps. Then came the crewed missions, each building upon the last. Apollo 7, in October of 1968, the first crewed flight of the redesigned command and service modules entered Earth orbit, proving the spacecraft was ready for human flight. Apollo 8, in December of 1968, a bold, accelerated mission to orbit the moon. Just months after the first crewed Apollo flight, Frank Borman, Jim Lovell, and Bill Anders became the first humans to leave Earth orbit and see the far side of the moon. Their Christmas Eve broadcast and the iconic Earthrise photo profoundly moved the world. Apollo 9, March 1969, tested the lunar module in Earth orbit, including rendezvous and docking maneuvers and spacewalks from the CM and LM, proved the LM was ready. Apollo 10, in May of 1969, the dress rehearsal for the landing, the LM descended to within 9 miles of the lunar surface. Before returning to the orbiting CM, it tested all phases of a lunar landing mission except the actual touchdown. By the summer of 1969, after years of relentless effort, technological development, and increasing risk, NASA and the nation were ready for the attempt that would define the decade. Apollo 11, the Eagle has landed. The mission, Apollo 11, the crew, Commander Neil Armstrong, Lunar Module Pilot Buzz Aldrin, and Command Module Pilot Michael Collins. Their objective, land on the moon. On July 16, 1969, the Saturn V rocket launched from Kennedy Space Center, carrying the hopes of millions. The journey to the moon took 3 days. Once in lunar orbit, Armstrong and Aldrin entered the lunar module, named Eagle, while Collins remained in the command module, Columbia, orbiting above. The descent was the most perilous part of the mission. As Eagle neared the surface, alarms sounded, indicating the onboard computer was overloaded. Quick thinking from guidance officer Steve Bales and the mission control team confirmed the alarms were due to a timing mismatch and could be ignored. Then Armstrong saw that the autopilot was steering them towards a boulder-strewn crater. With fuel running critically low, he took manual control, skillfully piloting the Eagle over treacherous terrain to a smooth landing spot in the Sea of Tranquility. The call from Armstrong crackled through speakers around the world. Houston, Tranquility Base here. The Eagle has landed. Relief erupted in mission control in Houston and across the globe. They had done it. They were on the moon. Several hours later, on July 20th, 1969, Neil Armstrong opened the hatch and carefully descended the ladder. With cameras rolling, he planted his foot onto the lunar surface. His words, relayed back to Earth, instantly became immortal. That's one small step for man, one giant leap for mankind. Buzz Aldrin joined him shortly after, describing the magnificent desolation. For over 2 hours, they explored the immediate vicinity, collected lunar samples, planted the American flag, and conducted experiments. All while Michael Collins orbited above alone, truly the loneliest man in the universe. Mission Control, the unsung heroes. While the astronauts were the faces of Apollo, the success of the program rested equally on the thousands of engineers, scientists, technicians, and controllers on the ground. particularly the team in mission control in Houston, led by figures like flight directors Gene Kranz, Chris Kraft, and Jerry Griffin. The flight controllers were the nerve center of every mission. They monitored every system, made critical decisions under unimaginable pressure, like during the Apollo 13 crisis, which we might touch on later, and guided the astronauts every step of the way. Their expertise, dedication, and teamwork were absolutely indispensable. The iconic image of the controllers, focused and determined, captures the immense human effort behind the technological marvel. Cultural impact and symbolism. The Apollo 11 landing was a moment of unparalleled global unity, and an estimated 600 million people, a fifth of the world's population at the time, watched or listened live. In a world deeply divided by politics and conflict, the moon landing was a shared human achievement. It demonstrated what was possible when resources, intellect, and will converged on a grand vision. Armstrong's words, "one small step for man, one giant leap for mankind," perfectly encapsulated the moment's symbolism. It was a single human taking a tentative step onto another celestial body, but it represented humanity's collective courage, ingenuity, and innate drive to explore the unknown. It wasn't just an American triumph, it was a triumph for the species. The impact on science, technology, and education was profound. The need for rapid innovation spurred countless technological advancements that spun off into everyday life, from computer chips and new materials to medical devices and satellite communications. The Apollo program inspired a generation of scientists and engineers, filling university classrooms and driving research in countless fields. Lasting legacy. While the immediate race element faded after the initial moon landings, the Apollo program continued through Apollo 17 in 1972, with each mission expanding the scope of lunar exploration and scientific discovery. The samples returned from the moon revolutionized our understanding of planetary formation. The lessons learned about operating in space were fundamental for everything that followed. Beyond the scientific and technological legacy, Apollo left an indelible mark on the American psyche. It was proof that seemingly impossible goals could be achieved through collective effort and unwavering determination. It represented an era of optimism, capability, and looking outwards. The image of humans walking on the moon remains a powerful symbol of human potential, a beacon of what we are capable of when we dare to dream big and reach for the stars. Space shuttle era and the expansion of human presence in orbit. All right. We've journeyed from the foundational Mercury and Gemini programs through the awe-inspiring triumph of Apollo in landing humans on the moon. That era was defined by a clear singular race to a specific destination. But what came next? After Apollo concluded in 1972, NASA and the American space program transitioned into a new phase, one focused less on planting flags on new worlds and more on making access to space routine, affordable, or so was the hope, and capable of supporting a sustained human presence. This phase was dominated by a revolutionary concept, the reusable spacecraft, the space shuttle. The vision for the space shuttle program emerged in the late 1960s and early 70s. After the intense, goal-driven effort of Apollo, there was a desire for a more flexible and cost-effective way to operate in space. The Apollo rockets and spacecraft were single-use vehicles. Once launched, they were either discarded or burned up on re-entry. The idea behind the shuttle was fundamentally different. A spacecraft that could launch like a rocket, orbit like a satellite, and land like an airplane, capable of flying multiple missions. This reusability was seen as the key to lowering the cost of space access and increasing the frequency of flights. Design and innovation, a reusable system. The Space Shuttle System, officially known as the Space Transportation System (STS), was an incredibly complex engineering marvel. It consisted of three main components. The orbiter. This was the iconic airplane-like vehicle that housed the crew, carried the payload in its large cargo bay, and performed the functions of orbiting and re-entering Earth's atmosphere. Vehicles like Columbia, Challenger, Discovery, Atlantis, and Endeavour became instantly recognizable symbols of the era. The orbiter used its own three powerful space shuttle main engines, SSMEs, during ascent. The solid rocket boosters, two large white boosters attached to the sides of the external tank. They provided the majority of the thrust during the first 2 minutes of launch. Crucially, they were designed to separate, parachute back to Earth, and be recovered from the ocean and refurbished for future use. The external tank, ET, the large orange tank that carried the liquid hydrogen and liquid oxygen propellant for the orbiter's SSMEs during launch. Unlike the SRBs in orbiter, the ET was not reusable. It would be jettisoned before the orbiter reached orbit and burn up in the atmosphere. The concept of integrating these components into a single launch system, with only parts of it being reusable, was a significant departure from previous rocketry. It represented a massive technological leap, requiring innovations in materials like the thermal protection system tiles on the orbiter's underside, propulsion, avionics, and structural engineering. Inception and early missions. The Space Shuttle program formally began development in the 1970s. The first orbiter, Columbia, was delivered to Kennedy Space Center in 1979, and after years of intense testing and preparation, the first mission, STS-1, launched on April 12, 1981. Piloted by John Young and Robert Crippen, STS-1 was a bold test flight, carrying only 2 crew members and proving that the complex system could indeed launch, orbit, and return safely to Earth. The successful landing at Edwards Air Force Base in California, looking very much like a conventional airplane landing, was powerful validation of the program's core concept. Early missions focused on proving the system's capabilities and deploying satellites. The shuttle quickly became NASA's primary launch vehicle for a wide range of payloads, from commercial and military satellites to scientific instruments. The large cargo bay, 15 feet in diameter and 60 feet long, allowed for the deployment of much larger satellites than previous rockets could handle. Key roles and capabilities. The shuttle wasn't just a satellite launcher. Its unique design allowed it to perform tasks previously impossible in space. Satellite deployment. The primary function in the early years, placing numerous satellites into orbit. Satellite retrieval and repair. Astronauts could use the shuttle's robotic arm, Canadarm, to capture satellites, bring them into the cargo bay, repair them in orbit, or bring them back to Earth for servicing. A famous example is the repair of the Solar Max satellite during STS-41-C in 1984. In-Orbit Science Laboratory, Space Lab. The European Space Agency developed Space Lab, a reusable laboratory module that can be fitted into the shuttle's cargo bay. This allows astronauts to conduct extensive scientific research in microgravity across various disciplines like biology, physics, and material science for extended periods during missions, often involving international crews. Launching interplanetary probes. The shuttle was used to launch several significant interplanetary missions, including the Magellan probe to Venus, the Galileo probe to Jupiter, and the Ulysses solar probe. While these required an additional upper stage rocket fired from the cargo bay, the shuttle provided the initial lift to Earth orbit. Hubble Space Telescope, HTS, deployment and servicing. Perhaps one of the most significant scientific contributions of the shuttle was its role in the Hubble Space Telescope. The shuttle deployed Hubble STS-31 in 1990 and, crucially, performed 5 subsequent servicing missions between 1993 and 2009. These complex missions involving multiple spacewalks, repaired and upgraded the telescope, transforming it into the unparalleled scientific instrument it is today. Without the shuttle's ability to rendezvous, capture, and allow astronauts to work on the telescope in orbit, Hubble's revolutionary discoveries would not have been possible. Preparing for the International Space Station, ISS. As the program matured, the shuttle's focus shifted significantly towards the construction and resupply of the International Space Station, its most enduring legacy. Tragedy and resilience, challenging moments. Despite its remarkable capabilities and achievements, the Space Shuttle program is also marked by profound tragedy, highlighting the inherent risks of spaceflight and the immense complexities of the system. These moments served as harsh reminders that making space routine was ambition, not a guaranteed state. The first tragedy struck on January 28, 1986, with the loss of the Space Shuttle Challenger during mission STS-51-L. Just 73 seconds after liftoff, the vehicle exploded, resulting in the deaths of all 7 crew members, including Krista McAuliffe, a teacher who was part of the Teacher in Space project. The investigation revealed that an O-ring seal in one of the solid rocket boosters failed in the unusually cold temperatures of the launch day, leading to a breach that ignited the external tank's propellant. The Challenger disaster exposed flaws not just in engineering, but also in decision-making processes and communication within NASA. The program was grounded for over 2 years while extensive investigations were conducted, safety protocols were overhauled, and the SRBs were redesigned. Flights resumed in 1988 with a renewed, albeit more cautious, emphasis on safety. The second tragedy occurred on February 1, 2003, when the Space Shuttle Columbia was lost during re-entry. At the end of mission STS-107, all 7 crew members perished. The investigation found that a piece of foam insulation had broken off the external tank during launch 16 days earlier and struck the leading edge of the orbiter's left wing, damaging the thermal protection system. This damage allowed hot atmospheric gases to enter the wing structure during re-entry, leading to its breakup. Like Challenger, the Columbia disaster highlighted critical technical issues and shortcomings in the organizational culture regarding identifying and addressing potential risks. The loss of Columbia led to another lengthy stand-down and further safety modifications. The shuttle program continued until 2011, but the focus increasingly narrowed to completing the ISS and ensuring the safety of the remaining flights. These tragedies were devastating blows to NASA and the nation, profoundly impacting public perception of spaceflight. They underscored the fragility of the technology and the bravery of the astronauts who knew the risks involved. Building the foundation, the International Space Station. Building the foundation, the International Space Station. Perhaps the most significant enduring contribution of the Space Shuttle program was its essential role in the construction of the International Space Station, ISS. The ISS is the largest structure ever built in space, and a testament to international cooperation. Its assembly, beginning in 1998, was a monumental task that relied almost entirely on the heavy lift capability and precision of the Space Shuttle. Over 30 shuttle missions were dedicated to building and resupplying the ISS. The shuttle's large cargo bay was uniquely capable of carrying the massive module segments, truss structures, solar arrays, and radiators that constitute the station. Astronauts used the shuttle's robotic arm and performed countless spacewalks to assemble these components in orbit, piece by painstaking piece. The shuttle served as the primary transport for station crews until after the Columbia accident. It continued to carry vital equipment and modules until its retirement. The construction of the ISS transformed the vision of sustained human presence in space from concept to reality. The station has been continuously inhabited since November of 2000, serving as a unique orbiting laboratory for scientific research in microgravity, Earth observation, and testing technologies for future deep space missions. The shuttle was the indispensable workhorse that made this permanent outpost possible, knitting together components from multiple countries into a single functioning entity. Legacy of the shuttle era. The Space Shuttle program officially ended in July 2011 with the landing of Atlantis on mission STS-135. Spanning 30 years and 135 missions, the program achieved incredible feats and pushed the boundaries of engineering and operations in space. It successfully deployed and repaired satellites, enabling groundbreaking scientific research through Spacelab and the servicing of Hubble, and most significantly, built the International Space Station. However, the program also fell short of some of its initial ambitious goals, making access to space routine and significantly reducing costs proved more challenging than anticipated. The system was inherently complex and expensive to operate and maintain. Two tragic accidents highlighted the significant risk that persisted despite sophisticated technology. Yet the legacy is undeniable. The shuttle enabled experiments and observations across diverse scientific fields thanks to Spacelab and missions like the Hubble servicing calls. It fostered unprecedented international collaboration through the ISS project, bringing together partners from the US, Russia, Europe, Japan, and Canada in a common endeavor. It demonstrated the challenges and possibilities of operating a complex, reusable space system and constructing large structures in orbit. The shuttle era was a period of transition. It moved the focus from reaching a single destination to establishing a persistent foothold in low Earth orbit. It taught invaluable lessons about operating complex hardware, managing risk, and the power of international partnerships in space. As NASA now looks towards returning to the moon and venturing to Mars, the experiences and infrastructure provided by the shuttle and the ISS form a critical bridge, building on the legacy of Apollo while paving the way for the next giant leaps. NASA's technological and scientific contributions beyond flights. So far, we've focused a lot on the dramatic, human-centric story of NASA, the race to the moon, the pioneering steps of Mercury and Gemini, the operational challenges and triumphs of the Space Shuttle, and the long-term presence enabled by the ISS. These missions, with the astronauts bravely pushing the boundaries of human endurance and capability, capture the public's imagination in a powerful way. But to understand the full scope of NASA's impact, we need to look beyond the images of humans in spacesuits and rockets blasting off. A vast, arguably even larger portion of NASA's work is dedicated to robotic exploration, scientific research, and technological development that doesn't involve putting people into space. These programs, often operating silently for years, have profoundly reshaped our understanding of the universe, our own planet, and have delivered countless practical benefits right here on Earth. They are the eyes, ears, and tireless probes of humanity, extending our senses far beyond where we can physically go. Looking down Earth science from orbit. One of the most crucial areas where NASA has made indispensable contributions is in understanding our own planet. While we tend to think of space exploration as looking out, a significant part of NASA's mission is looking down at Earth. Using satellites, NASA provides critical data on Earth's climate, weather patterns, ecosystems, natural resources, and natural disasters. Earth science missions leverage the unique vantage point of space to monitor global processes on a scale impossible from the ground. Satellites equipped with sophisticated sensors measure everything from sea level rise and ice sheet melting to forest coverage, atmospheric composition, and ocean temperatures. This continuous long-term data is vital for tracking climate change, predicting weather, managing resources like water, and responding to events like hurricanes, wildfires, and volcanic eruptions. Examples of these vital Earth-observing missions include Landsat program, a joint USGS-NASA program providing the longest continuous space-based record of Earth's land surface. Since 1972, Landsat images have documented everything from urban growth and deforestation to agricultural practices and geological changes, providing an invaluable historical archive. Aqua and Terra satellites, part of NASA's Earth observing system. These satellites collect data on Earth's atmosphere, land, ice, and water, helping scientists study climate change, carbon cycles, and energy balance. GRACE, Gravity Recovery and Climate Experiment, a pair of satellites that precisely measure changes in Earth's gravity field, allowing scientists to track movements of water, ice, and land masses, including groundwater depletion and ice sheet loss, followed by GRACE-FO, ISES-AT, Ice Cloud and Land Elevation Satellite, used laser altimetry to measure the height of ice sheets, glaciers, and sea ice, providing crucial data on polar ice dynamics and their contribution to sea level rise. The data from these missions is not just for scientists. It informs policy decisions, improves agricultural practices, aids urban planning, and enhances disaster preparedness and response worldwide. NASA's commitment to Earth science from space is fundamental to addressing some of the most pressing environmental challenges facing humanity today. Looking outward, astrophysics and deep space. If Earth science looks down, astrophysics looks gloriously outward. NASA has been a leader in using telescopes in space to observe the universe in ways impossible from the ground. Where Earth's atmosphere distorts or blocks light and other forms of electromagnetic radiation. The most famous example, and arguably one of the most significant scientific instruments ever built, is the Hubble Space Telescope, HST. Launched in 1990 and famously repaired and upgraded by Space Shuttle astronauts, Hubble has revolutionized our understanding of the cosmos. Orbiting above the atmosphere, it produces incredibly sharp images across visible, ultraviolet, and near-infrared light. Hubble's breathtaking pictures have captured the public's imagination, but its scientific impact is even greater. Hubble has been instrumental in precisely measuring the expansion rate of the universe and its age, discovering that supermassive black holes reside at the center of most galaxies, studying the formation and evolution of galaxies over cosmic time, observing the atmospheres of exoplanets, providing stunning views of stellar nurseries and the birth of stars and planetary systems. Hubble is just one jewel in NASA's astrophysical crown. Other key missions include Chandra X-ray Observatory, studies violent processes in the universe like supernova remnants, galaxy clusters, and black holes using X-rays. Spitzer Space Telescope, an infrared telescope that peered through dust clouds to reveal hidden stellar and galactic processes. James Webb Space Telescope, JWST, a partnership with ESA and CSA. JWST is the successor to Hubble, observing primarily in infrared light to study the first stars and galaxies, the formation of planetary systems, and the atmospheres of exoplanets with unprecedented detail. Fermi Gamma Ray Space Telescope studies the most energetic phenomenon in the universe, like gamma ray bursts and pulsars. These telescopes collectively have painted a picture of the universe that is far richer, more dynamic, and more mysterious than previously imagined. They allow us to trace cosmic history from the Big Bang to the potential for life beyond Earth, exploring other worlds, planetary science. While humans have only set foot on the moon, NASA's robotic probes have visited every planet in our solar system, providing intimate details about their compositions, atmospheres, geology, and potential for hosting life. This is the realm of planetary science missions. Some highlights of NASA's planetary exploration include Voyager program, launched in the late 70s. Voyagers 1 and 2 conducted a grand tour of the outer planets, Jupiter, Saturn, Uranus. and Neptune, revealing stunning details about their moons, rings, and magnetic fields. Both probes are now in interstellar space, continuing to send back data. Mars Exploration Program. NASA has a sustained multi-decade program of exploring Mars, utilizing orbiters, landers, and most famously rovers. Mars rovers, missions like Sojourner, part of the Mars Pathfinder, Spirit and Opportunity, Curiosity, and Perseverance have driven across the Martian surface, analyzing rocks and soil, looking for signs of past or present habitability, and even deploying the Ingenuity helicopter. They've confirmed that liquid water once flowed on Mars and characterized its environment in detail. Cassini-Huygens, a joint mission with ESA and the Italian Space Agency, Cassini orbited Saturn for 13 years, revolutionizing our understanding of the gas giant, its rings, and its diverse moons, particularly discovering subsurface oceans on the Enceladus and Titan with potential for life. Juno, currently orbiting Jupiter, studying its composition, atmosphere, and magnetic field to understand its formation and evolution. New Horizons, conducting the first ever flyby of Pluto and its moons in 2015, revealing a surprisingly active and complex world, is now exploring the Kuiper Belt. OSIRIS-REx visited asteroid Bennu and collected a sample of its surface material and is currently returning it to Earth for analysis. These missions don't just provide incredible images, they collect data on the physical and chemical processes shaping other worlds, helping us understand the origins and evolution of our solar system and the potential for life beyond Earth. They are scouts for future human missions and powerful drivers of scientific inquiry. From space to Earth, spin-off technologies. The intense technological demands of space exploration, both human and robotic, have spurred innovation that extends far beyond rockets and satellites. NASA has a long history of developing technologies that find applications in civilian life, commonly referred to as spin-offs. Examples include memory foam, originally developed for astronaut seating safety, LED lighting, used in space for plant growth, and now common in homes and industries. Satellite navigation, GPS. While primarily developed by the Department of Defense, NASA contributes significantly to its science and applications, and the underlying principles of satellite technology were driven by early space efforts. Advanced materials, developments in ceramics, alloys, and composites for spacecraft find uses in everything from aircraft to sports equipment. Medical technologies, miniaturization of sensors, advanced imaging and techniques, and telemedicine concepts developed for monitoring astronaut health have numerous terrestrial application. Water purification systems, developed for recycling water on long missions like the ISS. NASA actively facilitates the transfer of these technologies to the private sector, publishing an annual spin-off report detailing these contributions. This aspect of NASA's work demonstrates how investments in space exploration yields tangible benefits for society on Earth, improving quality of life, driving economic growth, and fostering innovation across various industries. In essence, NASA's non-manned programs are the bedrock of much of modern scientific discovery about the universe and our place in it. A significant source of technological advancement that benefits us all daily. While the astronaut missions capture the headlines, it is the tireless work of robotic explorers and orbiting observatories that constantly expands the frontier of our knowledge. Contemporary NASA and the path to Mars and beyond. All right. As we transition from the space shuttle era, which concluded in 2011, we arrive at the present day, a period for NASA and the American space program that is arguably as ambitious and transformative as the Apollo years, albeit with a different approach. The focus has shifted from establishing a routine presence in low Earth orbit, as the shuttle aimed to do, back towards deep space exploration, with the moon serving not just as a destination, but as a stepping stone, a proving ground for the ultimate goal, landing humans on Mars. This contemporary era is defined by bold new initiatives, significant technological advancements, and perhaps most notably, a fundamental shift in how space exploration is conducted, embracing extensive partnerships with both the private sector and international allies. Artemis program, returning to the moon and beyond. The cornerstone of NASA's current human spaceflight strategy is the Artemis program, named after the twin sister of Apollo in Greek mythology. Artemis aims to return humans to the lunar surface, but with a crucial difference from the Apollo missions of the 20th century. While Apollo was a sprint to plant a flag and return, Artemis is envisioned as building a sustainable presence on and around the moon. The primary goals of the Artemis program are multifaceted: landing the first woman and the first person of color on the moon. This highlights a commitment to diversity and inclusion in the next chapter of lunar exploration, establishing a long-term presence on the moon and lunar orbit. This involves building infrastructures like the Gateway space station and potential surface habitats, utilizing lunar resources, investigating and potentially using resources like water, ice, particularly at the lunar South Pole, which could be converted into rocket fuel or life support, paving the way for human missions to Mars. The moon serves as a critical testbed for technologies, procedures, and human endurance required for the much longer journey to the red planet. The Artemis program relies on several key components: Space Launch Systems, SLS, NASA's new heavy lift rocket, designed to be the most powerful rocket ever built upon completion of its various planned block upgrades. SLS provides the lift capability to send the Orion spacecraft, crew, and the necessary hardware to the moon. The first uncrewed test flight, Artemis 1, successfully launched in late 2022. Orion spacecraft, the crewed capsule capable of carrying astronauts farther than any previous human-rated spacecraft. Orion will transport the crew from Earth around the moon and back home. Gateway, a planned small space station in lunar orbit. Gateway will serve as a staging point for missions to the lunar surface, a science, outpost, and communications relay. Its modular design will allow for contributions from international partners and private companies. Human Landing Systems, HLS, the vehicle that will carry astronauts from lunar orbit, potentially from Gateway, down to the lunar surface and back up. Unlike the Apollo lunar module, HLS development is being primarily contracted to private companies, marking a significant change in approach. Lunar surface systems, including habitats, rovers, and power systems, needed to support sustained operations on the moon. The program is structured as a series of missions, starting with uncrewed tests, followed by crewed lunar flybys, Artemis 2, and ultimately leading to crewed landings, Artemis 3 and beyond. Artemis represents a generational undertaking, aiming to build an enduring capability for operating in deep space. New paradigms, private partnerships, and international collaboration. A defining characteristic of contemporary NASA is the increased reliance on partnerships with the private sector and international agencies. This is a significant departure from the Apollo model, where NASA acted primarily as the prime contractor, overseeing most aspects of design, development, and operations internally or through traditional cost-plus contracts with large aerospace firms. The rationale behind this shift is multifold: fostering a commercial space economy, leveraging private innovation and investment, potentially reducing costs, and allowing NASA to focus on cutting-edge research and deep space exploration. Commercial Crew Program successfully demonstrated the capability of private companies like SpaceX with the Crew Dragon and Boeing with the Starliner to transport NASA astronauts to and from the International Space Station. This has restored America's independent human spaceflight launch capability after the retirement of the shuttle and freed up NASA resources. Commercial Lunar Payload Services, CLPS. Under this program, NASA is purchasing payload delivery services to the lunar surface from commercial providers. This encourages the development of commercial lunar landers and infrastructure, allowing NASA to send scientific instruments and technology demonstrations to multiple landing sites frequently. Human Landing Systems, HLS. As mentioned, the critical component for landing humans on the moon is being developed under contract by private companies, currently primarily SpaceX. Space station commercialization. NASA is encouraging the development of commercial space stations in low Earth orbit to serve as successors to the ISS, allowing private ventures to handle LEO operations while NASA focuses on deep space. International collaboration remains crucial. The International Space Station continues to be a beacon of global cooperation involving the US, Russia, Europe, Japan, and Canada. The Artemis program is also built on international partnerships with countries like Canada, providing the next generation robotic arm for Gateway, and ESA providing the service module for the Orion spacecraft. Many nations have signed the Artemis Accords, a set of principles for peaceful and cooperative lunar exploration, signaling broad international interest on the moon. Technological leaps for future missions. Reaching Mars and sustaining a presence on the moon requires pushing the boundaries of technology further. While SLS and Orion are central to Artemis, future missions, especially to Mars, demand advancements in several key areas. Propulsion. Chemical rockets like SLS get us off Earth and towards destinations. But faster, more efficient propulsion is needed for crewed Mars transit. NASA and private companies are exploring technologies like electric propulsion used effectively on robotic missions, nuclear thermal propulsion (NTP), which could drastically reduce transit time to Mars, lowering crew exposure to radiation and microgravity. Space habitats and life support. Long-duration missions require advanced closed-loop life support systems that recycle water, air, and potentially waste more efficiently. Developing reliable, expandable habitats like inflatable modules for transit vehicles, gateway, and planetary surfaces is essential. In situation resource utilization, ISRU, the ability to live off the land by using resources found at the destination, like converting lunar or Martian water, ice into propellant and oxygen, is critical for reducing the mass that needs to be launched from Earth, making missions more feasible and sustainable. AI and automation. As missions become longer and farther from Earth, communication delays increase. AI and automation will be vital for monitoring spacecraft health, performing complex tasks, assisting astronauts, and managing surface operations with minimal real-time human input from Earth. Radiation shielding. Protecting crews from deep space radiation during long transits is a major challenge, requiring advanced materials and potentially active shielding techniques. Advanced robotics. Robots will play an increasing role alongside humans, assisting with construction, maintenance, resource extraction, scouting dangerous areas. Much of the research and development in these areas is ongoing, often involving partnerships with universities and the private sector. Challenges on the horizon. Despite the ambitious plans and technological progress, contemporary NASA faces significant challenges in pursuing its goals. Funding and budget consistency. Large-scale, long-term space programs like Artemis require sustained, predictable funding over many years. Shifts in political priorities and budget allocations from one administration or Congress to the next can cause delays, cost overruns, and uncertainty. Technical hurdles. Developing complex systems like SLS Orion, Gateway, and HLS is inherently difficult and prone to technical challenges as schedule slips, as seen throughout the history of these programs. Sustainability. Establishing a truly sustainable presence on the Moon and making Mars missions feasible requires not just landing once, but creating a long-term viable operational model, which involves significant infrastructure, logistics, and resource management challenges. Maintaining public and political will. Space exploration is expensive. Maintaining broad public and political support for ambitious, multi-decade programs is crucial, especially during times of economic or social challenges on Earth. Managing partnerships. Integrating diverse efforts from multiple private companies, each with their own timelines and business models. Coordinating with numerous international partners adds layers of management and technical complexity. Health and safety. Protecting astronauts from the harsh environment of deep space, including radiation, microgravity effects on the human body, and the psychological demands of isolation, remains a primary concern for long-duration missions. Navigating these challenges requires not only engineering prowess, but also strategic planning, effective management, and strong communication with stakeholders and the public. The current phase of NASA's journey is about building capability, learning how to live and work sustainably away from the Earth. The Moon is the nearest, most accessible proving ground for the technologies and operational experience needed to eventually take that monumental next step, sending humans to Mars. It's a future being built on the foundations of the past, guided by innovation, and increasingly reliant on a global network of partners, pushing the boundaries of what humanity can achieve in the cosmos. All right, folks, before we rocket onward into the next chapter of our space odyssey, let me take a moment to introduce you to something equally bold and crafted with a fiercely American spirit: Black Rifle Coffee. This isn't just your run-of-the-mill cup of coffee. Black Rifle Coffee is a veteran-owned company founded by former military personnel who bring the same grit, precision, and commitment to quality they had in service. Whether you prefer a robust dark roast to start your day or the smooth medium blend to steady your hand during these long, thoughtful musings, Black Rifle has it covered. Their coffee is roasted fresh on demand with blends and single origins that celebrate American craftsmanship and the entrepreneurial spirit. Each bag feels like a salute to the veterans who served and to all of us striving to tackle the day with clarity and fire. If you want coffee that fuels your passion for exploration or just keeps you sharp during late night writing sessions, Black Rifle Coffee is worth a try. Speaking of keeping sharp, have you ever considered how much your pen matters? Enter Skillcraft US government pens. These pens are not only precision engineered tools built for durability and performance, but they're also the official writing instruments trusted by government agencies nationwide. When you hold a Skillcraft pen, you're holding a piece of American heritage, reliable, smooth, and designed to meet the highest standards in some of the most critical environments. Whether jotting notes for the next big space mission or signing your own important documents, these pens deliver a writing experience that's effortless yet dependable. It's craftsmanship you can feel in your hand, just like the finest machinery that sends rockets skyward. So take a moment, brew a cup of Black Rifle coffee, and reach for a Skillcraft pen, because great ideas, like great journeys, deserve the finest tools. Before we continue our cosmic voyage, let's take a moment to celebrate creativity in another form, that of the poet's voice and the writer's hand. Have you ever felt an urge to capture your own thoughts, to spill dreams into verse, or simply find your unique rhythm in words? Allpoetry.com is a perfect place to start. It's a vibrant, welcoming online community where poets from all walks of life gather to share their work, receive feedback, and inspire one another. Whether you're a seasoned poet or a curious beginner, allpoetry.com invites you to explore the art of expression with a supportive network just a click away. From passionate sonnets to free-flowing prose poems, this site bustles with creativity, a digital campfire where voices blend in a chorus of imagination and reflection. Today's musings about humanity's great journeys spark new words inside of you. This is your space to let them fly. And speaking of capturing an inspiration, no creative journey is complete without the right companion for your thoughts and sketches. Enter the Moleskin Notebook, a trusted ally for writers, thinkers, and dreamers across generations. Known for its elegant design, durable cover, and buttery smooth pages, a moleskin is more than just paper. It's an invitation to record history, ideas, and fleeting moments of brilliance. Imagine jotting lunar impressions, sketching rocket blueprints, or composing your next poem, all with the tactile luxury of a moleskin. Its timeless craftsmanship connects you to a legacy of creators like Hemingway and Picasso, who found in their notebooks not only utility, but a form of reflection and self-discovery. So, whether you're inspired by space or by the human spirit, let allpoetry.com and Moleskin notebooks be your gateways to capturing the infinite, the finite. As we gaze towards the future of space exploration and innovation, it's fitting to recognize the visionaries who invest in tomorrow's breakthroughs today. Monarch Holdings International stands at the forefront of global investment, committed to fostering growth and innovation across industries that shape our destiny, including aerospace and cutting-edge technology. With a keen eye on transformative opportunities, Monarch Holdings supports pioneering companies pushing boundaries in flight, space exploration, and advanced research. Their strategic investments empower startups and established firms alike to develop revolutionary technologies that will fuel humanity's next great leaps, from sustainable space habitats to advanced propulsion systems. Monarch Holdings International exemplifies the spirit of visionary growth, embracing calculated risks to build a future where exploration and discovery are not just aspirations, but achievable realities. Their dedication aligns perfectly with NASA's mission to push humanity beyond known horizons, forging partnerships that turn bold ideas into tangible progress. In this era of rapid technological advancement and international collaboration, Monarch Holdings is more than an investor, it's a catalyst for innovation. When you consider the future of space, remember the companies that invest in it. Monarch Holdings International, enabling the journey that takes us beyond the stars. As we drift on this cosmic sea of stars, I find myself thinking about where we're headed next. And this Memorial Day, follow me in my musings at stephenlink.com and like and subscribe to my channel if you're so inclined. Throw me a donation. I don't have many debt or bills beyond car insurance and keeping myself alive, and nobody tells me what to think or what to say or influences me besides my immediate family and my fans and customers. So I am in a unique position to speak my mind and stay honest. I'm Stephen Link. Thanks for being here with me tonight. We're going to win.